In 2010, California initiated its high-speed rail project, a monumental undertaking. Split-screen, artists' rendering of the futuristic California high-speed rail next to a photo of a partially constructed, isolated viaduct in the Central Valley, designed to connect Los Angeles and San Francisco. The initial vision was clear and compelling, a modern, efficient train network that would complete the journey in under 3 hours. The projected cost was set at $33 billion. With an ambitious completion date of 2020, it was presented as a leap into the future of American public transportation, promising to reduce traffic congestion, lower carbon emissions, stimulate economic growth across the state. It represented a bold statement about progress and engineering capability, capturing the public's imagination with its scale and goals. Today, more than a decade past the original projected completion date, the reality of the California high-speed rail project looks profoundly different from its initial promise. The estimated cost has ballooned to over $100 billion for a scaled-down initial segment. And the full Los Angeles to San Francisco line remains an uncertain, distant prospect. The project has been plagued by continuous delays, legal challenges, escalating expenses. These issues have forced planners to revise timelines and budgets downward. The grand vision of a swift, transformative transportation artery has been replaced by a slow, incremental construction process. Many question if the original goals will ever be fully realized within a recognizable form. The stark contrast between ambitious blueprint and troubled execution is not an isolated incident. Across the globe, new airports, bridges, city-spanning transit systems, they are announced with great fanfare, backed by optimistic schedules and confident budget forecasts promising public benefit. Yet, as construction gets underway, these initial certainties often begin to dissolve. The public watches as deadlines are missed, costs spiral upwards, and the final product delivered is sometimes a compromised version of what was originally sold. This gap between plan and outcome is a persistent feature of mega projects. This recurring phenomenon raises a fundamental question about how these massive endeavors are planned and executed. Why do so many projects developed by experienced engineers and overseen by public agencies deviate so significantly from their initial course? The discrepancy is too common to be dismissed as simple bad luck or isolated mismanagement. It points toward something deeper within the system itself, a set of underlying factors and dynamics that consistently steer these complex undertakings away from their intended paths. Understanding this gap requires looking beyond the headlines of cost overruns and delays to examine the very structure of how such projects are conceived and brought to life. At the heart of any large construction project is a complex network of participants, a system of roles that interact, each with distinct responsibilities and objectives. The system begins with sponsors. Sponsors are typically public agencies or government bodies who initiate the project. They define the project's purpose, improve transportation, generate energy, revitalize an urban area. Sponsors secure political will and initial public support. Working alongside them are financiers, government treasuries, private banks, investment funds, international development organizations. Financiers provide the massive capital required. They prioritize financial viability and returns, shaping how risk is managed. Planners and engineers translate the high-level vision into a tangible blueprint. Urban planners assess fit and social and economic impacts. Civil engineers, structural engineers, geotechnical specialists. Engineers determine precise specifications, materials, construction methods. Their work follows physical laws, industry standards, and site-specific challenges. They produce detailed plans that guide every step. With a design in place, contractors execute the construction. Projects use a competitive bidding process. The selected primary contractor then manages a web of subcontractors, suppliers, laborers. Contractors aim to meet engineering specifications, while managing costs and timelines to ensure profitability. The owner-contractor relationship is defined by a legal contract. The contract outlines deliverables, schedules, and payment terms. The contract becomes the critical document that governs interactions. Regulators and other external stakeholders oversee the process. Regulatory agencies at the local level, state agencies, federal agencies. They enforce environmental protection, labor standards, and public safety. Regulators issue permits, conduct inspections, and can halt work for compliance issues. Community representatives, neighborhood associations, and advocacy groups. They raise concerns about noise, disruption, displacement, and long-term impacts. Their influence can trigger significant design changes, delays, or even project cancellation, making engagement a critical and often unpredictable element in the system. The life cycle of a large construction project unfolds through a series of distinct, sequential stages, each with its own set of goals and challenges. The journey begins with the concept stage. This is where the initial idea for the project is born. A government agency, a private developer identifies a need or an opportunity, easing traffic on a congested highway, increasing a port's capacity. During this phase, the focus is on defining broad objectives and scope. The output is typically a brief concept document. This initial concept provides political and strategic justification. Following the concept phase is the feasibility study, a critical go or no-go decision point. Planners analyze economic benefits versus costs. Engineers perform preliminary site investigations, difficult soil conditions, environmental constraints. Financial analysts build early funding and revenue models. The feasibility study filters out unworkable ideas. If feasible, the project advances to design and procurement, often overlapping. In design, architects and engineers develop detailed plans. Every element, from thickness of concrete walls to layout of electrical systems, is specified. Comprehensive blueprints and technical documents are produced. This translates the idea into a buildable plan. In parallel, procurement begins, selecting the main contractor who will build the project. The owner issues a tender, construction firms bid for the contract. Final cost and schedule are negotiated and codified. The project then moves to construction and handover stages. Contractors' workforce bring plans to life, coordinating thousands of workers, procuring vast quantities of materials, operating heavy machinery. Progress is monitored against the schedule and budget. Upon completion, the project moves to handover. The contractor transfers control to the owner or operator. Final inspections, testing of all systems. Official opening marks the culmination. When large projects go over budget and fall behind schedule, the most common explanation offered is that the initial estimates were simply wrong. This diagnosis of poor forecasting is an easy one to make in hindsight. At the outset, planners must predict costs for labor, materials, equipment years into the future, a task fraught with inherent uncertainty. Market prices for commodities like steel concrete can fluctuate dramatically due to global supply and demand shifts. Likewise, labor costs can change based on economic conditions, union negotiations. The models used to create these initial budgets, while complex, are ultimately built on assumptions about a future that cannot be known with perfect accuracy, creating a built-in margin for error from day one. These forecasting challenges extend beyond just financial costs. Estimating the time required for a multi-year construction project is equally difficult. Planners must create a schedule that sequences thousands of individual tasks, each with its own duration and dependencies. A delay in one critical activity, such as the pouring of a foundation, can have a cascading effect on the entire timeline. These schedules often fail to account for the true complexity of coordinating numerous subcontractors or the time it takes to resolve unforeseen technical problems. As a result, initial timelines are often more of an optimistic best-case scenario than a realistic projection of the work involved, setting the project up for perceived delays later on. However, attributing project failures solely to flawed estimates presents an incomplete picture. It treats forecasting as a purely technical exercise that simply needs better data or more sophisticated models. This view overlooks the fact that these initial estimates are not just predictions, they are also tools of persuasion. To get a project approved and funded, sponsors often have an incentive to present numbers that appear attractive and manageable. An estimate that is too high might kill a project before it even begins. This pressure can lead to what is known as optimism bias, where planners, whether consciously or not, underestimate costs and overestimate benefits to make the business case look stronger, embedding risk into the project's very foundation. Therefore, while poor estimates are certainly a factor, they are often a symptom of deeper issues rather than the root cause itself. They point to a systemic tension between the need for realistic planning and the political necessity of securing approval. If forecasts were simply technical errors, one would expect agencies to learn, over time, and improve their accuracy. Yet, the pattern of optimistic estimates persists across decades and continents. This suggests that the problem is not just about the difficulty of predicting the future. It is also about the environment in which those predictions are made, where optimistic numbers are often rewarded and realistic ones are penalized, leaving us with a gap in our understanding. Beneath the surface causes of poor forecasts lie more fundamental drivers. First, the incentive structure for project sponsors. To secure political approval and funding, a project must compete against other proposals for limited public funds. A project that appears cheaper and promises greater benefits has a much higher chance of being selected. This creates a powerful incentive to be optimistic. This phenomenon is known as strategic misrepresentation. Underestimating costs and overestimating benefits becomes a rational strategy for ensuring a project's survival. This initial optimism gets locked into the project's DNA. Once a government commits based on an optimistic budget, that number becomes the public benchmark. When costs inevitably rise, it's perceived as a failure of execution, not a flawed starting point. The system rewards the initial misrepresentation with approval, then punishes the implementers who grapple with reality. Another hidden driver is the mismatch between political and construction timelines. Politicians operate on short election cycles, needing visible results like groundbreaking ceremonies to secure re-election. In contrast, mega-projects can take a decade or more, dictated by engineering and logistical realities. Rushing early stages like design to meet a political deadline introduces errors that re-emerge later, where they are far more expensive to fix. The politician receives credit for initiating the project, but is often out of office when the consequences of their haste become apparent. The burden is passed on to future administrations, project managers, and ultimately the taxpayers. This separation of action and consequence embeds risk into projects from their inception. The persistent gap between the promise and the reality of large construction projects is not the result of isolated mistakes or individual failures, it is the logical output of the system itself. Cost overruns, chronic delays, compromised outcomes. These are not anomalies. They are predictable consequences of interacting incentives, feedback loops, and information delays. From the very beginning, the system incentivizes optimism over realism. The need to secure political approval and funding creates a competitive environment where understated costs and overstated benefits are rewarded, embedding a fundamental flaw into the project's DNA before any ground is broken. This is not a failure of forecasting, it's a rational response to the rules of the game. This initial flaw is then amplified by a series of hidden drivers: political incentives, optimistic forecasts, low bids, early lock-in, loop, cost overruns, scope cuts, reduced benefits. The short-term political cycle clashes with the long-term project cycle, pressuring leaders to rush and prioritize visible action over patient planning. The low-bid procurement model fosters an adversarial environment and perversely rewards the contractor who is most likely to be in financial distress, leading to corner-cutting and disputes. When problems inevitably arise from these starting conditions, negative feedback loops take over. The response to cost escalation is often scope reduction, which diminishes the project's value and can trigger a downward spiral of declining quality and benefit, ensuring the final asset is a shadow of its original promise. The entire process is constrained by the long shadow of early decisions, where the most critical choices are made with the least information, creating a path from which it is nearly impossible to deviate. The system lacks the capacity to learn and adapt. The true lesson is that these project failures are not a mystery to be solved, but a system functioning as designed, optimized for project approval, rather than for successful project delivery. This leaves one fundamental, unresolved tension. How can a society reconcile the need for democratic accountability, which operates on short electoral cycles, with the demand for patient planning, long-term planning, and technically sound planning that these generational projects require? Can a system be designed to serve both masters? You've been watching System Atlas, exploring how the world's systems really work. Share your comments below. See you in our next episode.